The world of iconic candy making reveals its power through three bold creations. We step inside the precise gelatin casting that shapes Haribo Gummy Bears, the intense sugar forging that defines every Jolly Rancher, and the rapid crystallization that builds each vibrant nerd's candy. Today, we trace these processes from raw ingredients to final form, uncovering the engineering discipline and flavor design that bring these candies to life. The process for Haribo Gummy Bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree cup walks. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, the hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Celsius and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees Celsius. To create multiple flavor variants, the unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees Celsius, with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. Polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the Wayfiller interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle, verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk: sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar-glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees C. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece-counting systems for final packaging. For bagged formats, vertical form-fill-seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. From sugar loading to pallet stacking, each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are metered using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing Nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. A fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, the spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 degrees to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills 2 parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of 2 flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or preformed containers, sealed, and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blends, pre-mixed according to a proprietary formula, includes a combination of salt, natural, and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. It all starts long before the fries hit the fryer. Behind the golden arches and the crunch of each familiar bite lies a factory system of immense complexity, one that spans agriculture, chemistry, precision slicing, and global logistics. McDonald's French fries may seem like simple potato sticks fried in oil, but the reality is that each one is the end product of a deeply controlled, highly optimized manufacturing process. And what most people don't realize is how much of that process is hidden in plain sight at the factory level, where McDonald's and its contracted processors manage every microscopic detail to make sure every fry, from Tokyo to Texas, tastes exactly the same. The process begins with the potatoes themselves, but not just any potato will do. McDonald's fries are made almost exclusively from specific varieties, most commonly the Russet Burbank, the Shepherdie, the Ranger Russet, and the Umatilla Russet. These varieties are chosen for their long shape, high starch content, and relatively low sugar levels, which are crucial for creating that ideal, crispy exterior and soft interior that define McDonald's fries. What McDonald's doesn't advertise is how deeply it's involved in the agricultural side of this operation. The company works directly with contract farmers, some of whom grow nothing but McDonald's potatoes on thousands of acres of land. These farmers follow strict growing guidelines dictated by McDonald's and its primary potato processors like J.R. Simplot and Lamb Weston. Everything from the irrigation schedule to the exact time of harvest is data-driven and monitored by field agronomists. Why so much control? Because if the potato's sugar level is too high, the fry will burn in the oil, turning dark brown instead of golden yellow. If the potato has too much moisture, it will steam instead of crisping. And what's often hidden from view is the extensive sorting and testing done before the potatoes even make it to the processing plant. Once harvested, potatoes are stored in high-tech facilities that carefully regulate humidity, airflow, and temperature, often between 45 degrees Fahrenheit and 50 degrees Fahrenheit, to prevent sprouting and sugar buildup. At this stage, the potatoes go through a phase known in the industry as curing, which helps them develop a tougher skin and reach the desired sugar-to-starch balance. McDonald's factories don't reveal much about this curing phase, but it's one of the most critical elements to ensure that the potatoes will fry up properly when they finally reach your tray. When potatoes arrive at a McDonald's processing facility, many of which are run by their longtime partner, Simplot, they're subjected to a barrage of sorting and quality control tests. The first step is visual sorting, where cameras and AI-powered systems scan each tuber for defects, bruises, blemishes, and anything that would impact final appearance. Those that don't meet the exact standards are removed. But what most people don't know is that the internal sugar content of the potato is also tested using sophisticated near-infrared scanners. Potatoes with sugar levels, even slightly outside of spec, are rerouted to other uses or discarded entirely. After sorting, the potatoes are cleaned in an intense, multi-stage washing process. They pass through flumes, essentially water slides, where dirt and debris are blasted away by high-pressure jets. Then, they're scrubbed mechanically in abrasive drums and visually re-inspected. By the time a potato reaches the peeling phase, it's already undergone more inspections than most food products receive in their entire life cycle. Why? Because McDonald's doesn't just want quality, they want standardization. Each fry must look and taste the same, regardless of whether it's cooked in Malaysia or Montana. Peeling is done using a high-pressure steam system. The potatoes are loaded into a sealed vessel and blasted with superheated steam for just a few seconds. This causes the skin to loosen rapidly. As soon as the pressure is released, the skins separate and are rinsed away. What remains is a completely peeled, pristine potato ready for slicing. But the slicing is not random. It's done by a process far more mechanical and mathematical than most people would guess. The peeled potatoes are shot at extremely high speeds, up to 60 miles per hour, through a grid of stainless steel cutting blades known as a water knife. These blades slice the potatoes into precise lengths and widths, typically around 0.28 inches thick and up to 3.5 inches long. The water jet ensures minimal friction and deformation, which is especially important for keeping the fries straight and uniform. In the background, software algorithms are constantly adjusting cutter feed rates and blade sharpness to match the physical properties of each batch of potatoes. But here's where the first secret really kicks in. Once the fries are cut, they don't go directly into oil. First, they're blanched in hot water, typically between 160 degrees Fahrenheit and 170 degrees Fahrenheit, for several minutes. This is a crucial but rarely discussed step. The blanching process serves multiple purposes. It removes excess sugars to reduce browning during frying. It gelatinizes some of the starches to create a smoother exterior. And it partially cooks the interior to ensure the fry finishes with the right soft texture after final frying in store. What's less known is that this water may be treated with additives, like citric acid or sodium acid pyrophosphate, to preserve the color of the fries and prevent graying during storage. After blanching, the fries are rapidly dried in a high-powered air system. This air drying tunnel removes surface moisture to prepare the fries for the next step, the first fry. Yes, that's right. McDonald's fries are fried twice, but the first time doesn't happen in your local restaurant. It happens at the factory. The pre-frying phase is done in massive vats of vegetable oil, heated to around 375 degrees Fahrenheit. The fries are cooked for just 45-60 seconds, long enough to create a light outer shell, but not to fully cook the interior. This brief fry locks in the shape and starts forming that distinct McDonald's fry texture. After this flash fry, the fries go straight into a blast freezer. In a matter of seconds, their temperature is dropped from over 300 degrees Fahrenheit to well below 0 degrees Fahrenheit. This locks in moisture, halts cooking, and extends shelf life for months. The result is what's known in the industry as a par-fried product, partially cooked, frozen, and ready to finish. Once the freshly par-fried McDonald's fries exit the industrial fryers, still golden but only partially cooked, they enter one of the most carefully engineered steps of the entire production process: freezing. This phase is far from ordinary. The secret to locking in that signature McDonald's fry texture and color involves cryogenic speed, airflow science, and microcrystal management. Every fry is treated not as a raw potato product anymore, but as a finished structure in progress, one that must be preserved in a state of suspended readiness until it is reanimated in the deep fryers of restaurants across the globe. The fries are conveyed directly from the oil fryers to a blast freezing tunnel. This isn't your average cold room. It's a highly pressurized, continuous flow freezer capable of dropping product temperature from over 350 degrees Fahrenheit to well below 0 degrees Fahrenheit in less than 5 minutes. This rapid freezing is key to quality preservation. Why? Because fast freezing forms tiny ice crystals within the fry's cellular structure. These microcrystals are less damaging than larger, slower formed crystals that rupture cell walls and lead to mushy textures when cooked. McDonald's suppliers invest heavily in ultra-fast freezing systems to ensure that every fry maintains its structural integrity from factory to fryer. Inside the freezer, conveyor belts carry fries through multiple zones where the temperature is dropped in controlled increments. Powerful fans circulate ultra-cold air in a laminar flow pattern, creating a uniform freezing effect across each fry's surface. Sensors inside the chamber measure air velocity, temperature, product thickness, and moisture levels to adjust fan speeds and refrigerant input in real time. The goal is a fully frozen product with a moisture content that stays just right. Not too dry, not too icy, so that the final fry will puff and crisp just the way McDonald's demands. But before these frozen fries are boxed and shipped, one more step takes place. One that most consumers never think about: anti-clumping treatment. Because McDonald's fries are thin and uniform, they're at risk of sticking together once frozen, especially in high moisture environments. To counter this, a microscopic layer of dextrose is sometimes applied after blanching and before freezing. This coating is not added for sweetness. It's there to assist with color development and minimize the chance of oxidation during storage. It also subtly enhances surface crispness during the final fry. In some factories, an even more specialized process is used. A combination of sodium acid pyrophosphate and citric acid may be sprayed on the fries pre-freezing to lock in that golden hue. This solution prevents enzymatic browning and further stabilizes the fry's color even after months in frozen storage. It's a step that might seem unnecessary, but in the McDonald's system, where fries are shipped internationally and cooked under variable conditions, it's part of the formula for total consistency. Once fully frozen and treated, the fries are transported to the packaging line. This stage is fast, automated, and highly controlled. Fries are weighed using combination scales, which use dozens of small buckets to calculate the perfect load. Whether it's 2.5 pounds bulk bags for food service or 10 pounds cartons destined for regional McDonald's distribution centers. Each batch is fed into high-speed form-fill-seal machines where plastic liners are formed from reels of film filled with frozen fries and sealed airtight. Oxygen is flushed from the bag and replaced with inert gases like nitrogen to extend shelf life and prevent freezer burn. Each bag is labeled with batch codes, facility information, and freeze dates. These bags are then placed into corrugated cartons, which are automatically stacked onto pallets and shrink wrapped. The pallets are scanned into the facility's warehouse management system and stored in vast, temperature-controlled storage rooms maintained at below -10 degrees Fahrenheit. From here, they wait, sometimes just days, other times weeks, before being dispatched to a McDonald's distribution hub. What's rarely discussed publicly is just how advanced the inventory system is. Every pallet of fries is tracked from the moment it's boxed to the moment it's unloaded in a restaurant kitchen. If there is ever a concern about quality, contamination, or shipping damage, McDonald's corporate and their suppliers can trace every fry down to the production line, fryer, and time of day it was processed. This traceability isn't optional. It's embedded in food safety protocols, legal compliance systems, and global quality assurance audits. When the fries finally arrive at a McDonald's restaurant, they're still not done. They are stored in walk-in freezers until ready for use, where conditions must be monitored and logged to ensure the frozen state is never compromised. A fry that partially thaws and refreezes will develop ice crystals, lose crispness, and underperform in the fryer. Every crew member in the kitchen is trained to handle the frozen product delicately, shaking bags to loosen clumps, never overloading the baskets, and minimizing the time between freezer and fryer. And now, the final fry begins. In store, the frozen fries are dropped into preheated oil, specifically a blend of canola oil, corn oil, and soybean oil. However, what most consumers don't know is that this oil is carefully filtered and changed according to a strict schedule. Filtration systems inside each fryer remove particles of carbonized food and prevent oil breakdown, extending usability while maintaining the clean, light flavor McDonald's demands. The oil is tested multiple times daily for free fatty acid levels, color, and foaming to make sure it hasn't deteriorated. If any reading goes outside McDonald's specifications, the oil is discarded and replaced. The frying process in store lasts precisely around 3 minutes at roughly 168-175 degrees Celsius, depending on local settings and fryer model. During this time, the moisture inside the fry flashes to steam, puffing the interior slightly while the exterior rapidly crisps. Those tiny air pockets created by the factory blanching and flash frying now finish the transformation. And the secret to McDonald's uniform texture? It's those pre-engineered starches and exact cook times. When done properly, the fry is lightly golden, stiff enough to hold its shape, and just soft enough inside to match the one you had years ago. Seasoning is also precisely measured. As the fries are shaken from the fryer basket, they're dropped into a stainless steel holding tray and dusted with a uniform dose of pure, fine-grained salt. The salt granules used by McDonald's are specially selected for size and shape, large enough to adhere to the surface oil, but fine enough to dissolve quickly on the tongue. Shakers are calibrated, and portion control guidelines ensure consistency across locations. And here's the last hidden layer of control: the fry holding time. McDonald's dictates that fries must be served within a very specific window after cooking, usually no more than 7 minutes. After that, they're discarded, even if they appear fresh. This strict timer is part of the reason your McDonald's fries are often hot, crisp, and consistent. It's also one of the reasons you'll rarely see a fry sitting under the heat lamp for long. While most McDonald's fans recognize the signature taste of their fries almost instantly, few understand just how orchestrated that flavor really is, or how it's achieved through a global network of tightly controlled suppliers, additive strategies, and ingredient choices designed to replicate a flavor memory baked into the global food consciousness. The story of McDonald's French fries isn't just about potatoes, oil, and salt. It's about manufacturing identity, reproducing the exact same sensory experience for billions of customers each year, regardless of where or when they eat them. To understand how McDonald's does this, you need to look beyond just the factory floor. Behind the scenes is a system of global standardization that governs everything from agricultural inputs to packaging films. Simplot, McCain, and Lamb Weston are the primary suppliers of McDonald's fries, and each operates massive, dedicated processing plants, some of which process hundreds of thousands of pounds of potatoes per day, exclusively for McDonald's. These facilities are synchronized with a global specification book that dictates the required fry length, thickness, shape, sugar tolerance, moisture range, oil absorption, and post-fry texture. And then there's the flavor. Many consumers don't realize that McDonald's French fries are subtly flavored before they ever reach the restaurant. For decades, McDonald's fries were cooked in beef tallow, a rendered fat from cattle. that gave them their distinctive, rich flavor. But by the 1990s, amid rising health concerns and cholesterol awareness, McDonald's phased out animal fats and replaced them with vegetable oils. This change had a major impact on taste, prompting backlash from loyal customers who noticed the difference almost immediately. What most people don't know is how McDonald's responded to that backlash, not by returning to beef tallow, but by recreating its flavor synthetically. Today, the par-fried fries that leave the factory are flavored with a natural beef flavor additive. This additive is applied during the pre-frying stage or infused into the frying oil and contains hydrolyzed wheat and milk derivatives. It's designed to replicate the rich, meaty aroma once delivered by tallow, but without using actual beef fat. This additive is one of the most closely guarded secrets of the entire process. It's what gives McDonald's fries that faint umami backbone that makes them taste savory in a way that purely plant-fried potatoes often do not. And while this additive is labeled as natural flavor on ingredient lists, its composition is highly engineered by flavor chemists and tested repeatedly to ensure it holds up under freezing, frying, and heating conditions in restaurants. The flavor system doesn't stop at aroma. Texture plays a role too. McDonald's fries are engineered to crisp on the outside and remain soft in the middle, and achieving this consistently across markets is an engineering challenge. The crinkle-like effect of the outer skin is partly due to starch modification. Some potato slices are lightly coated with a thin layer of modified starch before freezing, an invisible layer that reacts in the fryer to create a delicate crust, locking in moisture and helping the fry maintain a longer crisp life under heat lamps. This crust is not easily visible, but it is critical. Without it, fries would quickly become limp and oily within minutes of cooking. With it, they hold their shape, resist sogginess, and retain that gentle crunch even as they cool. And although McDonald's does not add batter to its fries, as some fast food chains do, this ultra-thin layer of modified potato starch acts in a similar way, without compromising the all-natural image. Regionally, the manufacturing process must adjust for climate, regulation, and local preference without changing the end result. For example, in India, McDonald's fries do not contain the beef-derived flavoring found in the US to respect dietary and religious restrictions. In Muslim-majority countries, fries may be certified halal and produced in dedicated facilities to ensure separation from non-compliant products. These adjustments require dedicated supply chains, custom formulation runs, and regular taste panels to ensure that the final fries remain indistinguishable from their global counterparts in look, feel, and taste. Flavor consistency is upheld using trained sensory teams who sample fries from different global markets and compare them to reference standards kept in controlled storage. These panels evaluate crispness, oil profile, salt adhesion, internal moisture, mouthfeel, and aroma. If a discrepancy is detected, for example, fries from a factory in Southeast Asia are crispier than those in the US, engineers can investigate and recalibrate oil composition, blanching temperature, or drying time to rebalance the product. And there's more. Packaging. Even the packaging for McDonald's fries is a product of manufacturing science. The familiar red carton is designed not just for branding, but for thermal control and grease resistance. The paperboard is treated with a food-safe coating that prevents oil soak through, and the shape of the carton, with its slightly flared mouth and deep vertical pocket, is calibrated to maintain heat without trapping steam. Fries are less likely to sweat inside these containers compared to traditional closed boxes, which helps preserve texture even during transport or delivery. In the supply chain, those frozen fries move through an equally engineered logistics network. From factory freezers, they're shipped in refrigerated trucks, often under continuous GPS and temperature tracking. Distribution centers store them in walk-in freezers maintained below -10 degrees Fahrenheit, and restaurant deliveries are timed and logged to minimize thaw risk. McDonald's tracks fry inventory down to the store level, forecasting usage based on PCPOS data, and adjusting regional deliveries in real time. If a freezer malfunctions, the system flags the at-risk batch immediately, allowing a preemptive product pull before a customer ever notices. Back in the restaurant, staff are trained using digital timers, fry chart cards, and standardized scoops to portion, salt, and serve the fries. McDonald's restaurants even perform fry station audits to check adherence to hold times, oil filtering frequency, and batch rotation. These audits happen regularly, often without notice, and are tied to store performance metrics. Managers are held accountable for fry quality just as they are for speed of service or cleanliness. Despite all this control, McDonald's fries do have one unavoidable weakness: time. Even with starch systems, flavor additives, and optimized packaging, fries lose their peak texture within minutes. That's why McDonald's limits the hold time in the warmer to around 7 minutes. After that, fries are discarded, still edible, but no longer acceptable by brand standards. This results in significant waste, but it also maintains McDonald's reputation for fresh tasting fries, even if they were frozen and processed weeks earlier. So what are McDonald's factories really hiding? Not deception, not shortcuts, but the scale and precision of industrial food science operating behind something as simple as a fry. The way a potato is selected, how it's processed, flavored, partially cooked, frozen, stored, shipped, fried again, and even salted. All of it is engineered to deliver that one familiar experience. Hot, golden fries that snap slightly when bitten, give way to a tender interior, and leave a subtle beefy aroma in their wake. What they're hiding is just how much work it takes to make something look so effortless. The real secret of McDonald's fries is that there are no accidents. Every element, from starch composition to carton geometry, is designed. And in a world where people crave predictability in their favorite foods, that's exactly the point. The next chapter in McDonald's French fry production isn't just about improving what already exists. It's about redefining how the entire process can evolve under new technological, environmental, and consumer health expectations. While the current system has been fine-tuned over decades to deliver uniformity and mass appeal, the future introduces challenges that can't be solved by simply optimizing old methods. Automation, artificial intelligence, sustainability, and evolving nutritional preferences are all converging to push McDonald's and its processing partners into the next phase of fry manufacturing. One of the most notable developments is the rise of advanced automation and AI-driven process control. In modern McDonald's fry facilities, machine learning algorithms are already being piloted to monitor real-time data from every stage of production. Sensors embedded along the slicing lines, blanches, fryers, and freezers send continuous streams of information: potato dimensions, sugar content, moisture loss, oil flow, fry color, and more. These AI systems analyze the incoming potato crop and dynamically adjust settings like blade calibration, blanching time, or oil temperature to match variations in raw material quality. Instead of relying on preset recipes, the system now learns and adapts, helping reduce inconsistencies and food waste. In parallel, robotics are making inroads not just in manufacturing, but inside McDonald's restaurants themselves. Frying stations in pilot stores are being equipped with robotic arms or automated baskets that load, cook, and shake fries with no human input. This standardizes cook time and reduces operator error, ensuring that each batch is fried exactly to spec, regardless of shift or staff turnover. For McDonald's, this reduces labor costs, improves food safety, and eliminates variability in fry texture and temperature. Sustainability is also driving significant changes. One of the key pressures on the current model is oil usage. While McDonald's already employs rigorous oil recycling and filtration protocols, new systems are being trialed that extract even more particulates and extend oil life significantly without affecting flavor. Some suppliers are exploring high-efficiency fryers that use vacuum environments to lower frying temperatures, reducing oil absorption and energy usage. McDonald's is also quietly funding research into lower oil par-frying methods that could replicate crispiness using air-based thermal systems, potentially paving the way for a future where fries are air-fried in-store rather than deep-fried. Water usage is another sustainability frontier. The massive amounts of water used in washing, blanching, and rinsing potatoes are being addressed through closed-loop recycling systems and precision spray technologies. Instead of full immersion, some newer systems use high-pressure misting to clean and treat potato surfaces, cutting water usage by up to 40% per ton of potatoes processed. Every gallon saved matters when facilities are producing millions of pounds per week. Health consciousness among consumers is also influencing the future of McDonald's fries. Although the company has already shifted to trans fat-free oils, the next step may involve reducing sodium or introducing new seasoning options. Internally, there's ongoing experimentation with lower sodium salts that maintain the same flavor perception with less actual sodium chloride. Other ideas under consideration include sweet potato or blended vegetable fries, though any change to the core offering would require monumental testing to avoid alienating loyal customers. A crisp snap, a creamy melt, and a perfect balance of chocolate and wafer. Kit Kat is more than a candy bar. It's a confectionery icon, loved worldwide and instantly recognizable for its 4 slender fingers and clever tagline. Kit Kat stands as a shining example of how precision engineering, food chemistry, and high-speed automation can come together to craft something remarkably simple and yet technically intricate. To understand how Kit Kat is made in a factory, we have to start with its dual nature, half chocolate, half wafer. Each must be manufactured independently with extreme care, then combined at the right moment to create a product that tastes the same, whether it's made in Japan, the UK, or Canada. The process begins with the preparation of raw ingredients, and the base of it all is wheat flour, used for the crispy wafers. This flour is stored in towering silos, aerated and filtered to remove dust and contaminants. It's pneumatically conveyed to the mixing room, where it's combined with sugar, palm or sunflower oil, milk powder, salt, baking powder, and water. These ingredients are deposited into large, jacketed horizontal mixers, which knead them into a consistent, homogeneous dough. At this stage, automation systems monitor dough temperature and hydration levels, adjusting mixer speed and timing accordingly. Once the dough is ready, it's extruded into thin sheets. This happens on massive wafer sheet lines, flat conveyor belts, where rollers press the dough into sheets less than 2 millimeters thick. These sheets move through high-capacity baking ovens that use convection heat to evenly cook them. These ovens stretch over 50 feet long, operating at temperatures around 180-200 degrees. Each wafer sheet bakes for less than 2 minutes, but emerges dry, crisp, and golden, ready for layering. Now comes one of the most signature features of the Kit Kat, the layered wafer structure. Each wafer sheet is passed through a slathering station, where a precise amount of wafer cream, a chocolatey, fat-based paste, is applied to its surface. This cream, made from finely ground sugar, fats, milk solids, and cocoa powder, serves as both flavor and adhesive. Multiple layers of wafers and cream are stacked, typically 3 wafers and 2 cream layers, forming a block known internally as a wafer book. These wafer books are pressed under light pressure and sent through cooling tunnels to stabilize the cream. Once firm, they are sliced into individual fingers using ultra-sharp guillotine blades or water jet cutters. Each finger is a perfect rectangle, dimensionally identical to ensure they fit precisely into the chocolate molds in the next stage. Meanwhile, chocolate production is running in parallel. Kit Kat uses milk chocolate, which must be refined and tempered to perfection. The chocolate begins with cocoa liquor, cocoa butter, milk powder, and sugar, all blended together in mixing tanks. From there, the mixture is passed through refiners, a series of large rollers that crush and flatten the mixture into particles smaller than 20 microns. This size is critical to achieving the smooth mouthfeel expected of high-quality chocolate. After refining, the mix enters conching machines, giant heated vats where the chocolate is stirred, aerated, and aged for several hours. This removes bitter volatiles, improves texture, and develops flavor. Once conching is complete, the chocolate is tempered, a precise process of heating, cooling, and reheating the chocolate to promote the formation of stable cocoa butter crystals. Without this step, the chocolate would be dull, soft, or prone to blooming. Tempered chocolate has a shiny finish, satisfying snap, and melt-in-your-mouth consistency. Now the chocolate and wafer fingers are ready to unite. This happens on a molding line. First, plastic or stainless steel molds are warmed slightly and filled with a thin layer of tempered chocolate. This bottom layer forms the base of the Kit Kat. Then, the pre-cut wafer fingers are robotically placed onto the chocolate-filled molds. Another dose of chocolate is deposited over the top, fully enrobing the wafer fingers and completing the bar structure. The filled molds pass through a vibration table to remove air bubbles and ensure complete coverage. From there, they travel through a cooling tunnel, a refrigerated chamber where the chocolate crystallizes and solidifies. By the time the molds exit, the Kit Kat bars are fully formed, firm, and ready to be demolded. Demolding is fully automated. Each mold is flipped, and a gentle mechanical tap releases the bars onto conveyor belts. The now empty molds are cleaned, sterilized, and recirculated back into the system. The Kit Kat bars now move to quality inspection. Vision systems equipped with high-speed cameras scan every bar for size accuracy, surface defects, cracks, or incomplete coatings. If anything is off-spec, that bar is removed from the line. Approved bars continue on toward the flow wrapping station. Packaging is a crucial part of the Kit Kat experience, not just for branding, but also for shelf life. Each bar is wrapped in metallized plastic film that acts as a barrier to light, oxygen, and moisture. The flow wrappers operate continuously. Bars are fed onto belts, aligned by guide rails, and pushed through a forming collar where the film is wrapped around them and sealed with heat-sealing jaws. Wrapped bars are then grouped into multi-packs or secondary trays, depending on customer requirements. Robotic arms or pick-and-place machines assemble the bars into display-ready formats. These units are then placed onto pallets using automated palletizers and stretch-wrapped for transport. Every step of this process is monitored by SCADA systems and connected sensors. Mixing temperatures, dough moisture, oven humidity, chocolate viscosity, flow speeds, and packaging integrity are all logged in real time. If a parameter drifts outside the set range, alerts are triggered and corrective action is taken immediately, either by automatic control or operator intervention. Meanwhile, samples from every production lot are pulled and sent to the on-site quality assurance lab. Here, technicians run texture analysis, moisture content testing, shelf stability trials, and most importantly, sensory evaluations. Trained tasters assess whether the product matches the official profile: crisp but not dry, sweet but not cloying, and a melt that delivers the cocoa hit right before the wafer crunch. Beyond quality, Kit Kat factories are also designed with hygiene and allergen safety in mind. Separate lines may be maintained for peanut-free or gluten-free variations, and full allergen switchover protocols are implemented if recipes change. Stainless steel surfaces, clean-in-place systems, air filtration, and pressure-zoned rooms ensure that each environment is sanitary and safe. Sustainability is also an emerging pillar of Kit Kat's production. Many factories now source Rainforest Alliance certified cocoa, and water and energy recovery systems are implemented to reduce waste. Chocolate scraps and wafer trim are collected and reprocessed, either reused in internal production or recycled into other food streams. From raw wheat and cocoa beans to precision molded chocolate fingers, the production of Kit Kat is a dance of science and craftsmanship. It's easy to take for granted, something you grab at the store, tear open, and snap into without a second thought. But behind every bar is an extraordinary feat of coordination, timing, and innovation. It's the result of countless variables, all controlled within narrow limits, to ensure that when you have a break, you're rewarded with the exact flavor, texture, and snap you expect. Golden foil, delicate layers, creamy filling, and a whole hazelnut at the core. Ferrero Rocher is the epitome of premium chocolate craftsmanship. But what seems like a luxurious, handcrafted treat is actually the result of one of the most precise and sophisticated chocolate manufacturing operations in the world. Produced by the Italian confectionery giant Ferrero Group, Ferrero Rocher is a marvel of layered architecture and synchronized automation. And to truly understand how it's made, we must step inside the walls of one of their advanced, high-security confectionery plants. It all begins with the hazelnut, Ferrero's signature ingredient. The company is one of the largest consumers of hazelnuts globally and maintains close relationships with farmers across Turkey, Italy, and Chile. Only whole, uniform, high-grade hazelnuts are accepted for use in Ferrero Rocher. Upon arrival at the processing facility, the hazelnuts are cleaned to remove debris, shelled, and subjected to multiple rounds of size grading and visual inspection, both by machine and by human eyes. The hazelnuts are then gently roasted in continuous drum roasters. These large, rotating cylinders apply indirect heat to evenly roast the nuts without scorching them. Temperature and time are tightly controlled, typically around 150-160 degrees Celsius for 15 to 20 minutes. The goal is to enhance the nut's natural oils and flavor without damaging the internal structure. Once roasted, the nuts are cooled rapidly to halt the cooking process, then transferred to storage under nitrogen to preserve freshness. With the hazelnuts ready, attention turns to the wafer shell, the crisp, spherical layer that surrounds each nut. The wafer is made from a batter of wheat flour, water, sugar, oil, and leavening agents. The batter is deposited onto heated hemispherical molds in automated wafer baking machines. These molds close like clamshells, sealing and cooking the wafer until it forms a hollow, thin sphere. This process takes only seconds, and each wafer shell is then cooled, trimmed, and conveyed to the filling station. Now we move to the cream filling. This smooth, chocolate hazelnut cream is made using a proprietary blend of ingredients: cocoa, milk powder, sugar, and hazelnut paste. The hazelnut paste is prepared by finely grinding roasted hazelnuts into a silky nut butter, then blending it with cocoa solids, vegetable oils, and emulsifiers. The mixture is heated, homogenized, and passed through conching units to develop a smooth texture and balanced flavor. At this point, multiple streams converge. A whole roasted hazelnut is placed in the center of each wafer hemisphere. Then, a precise amount of the chocolate hazelnut cream is deposited into the cavity, encasing the nut. The wafer sphere is closed by joining two halves together with a light pressure and a ring of filling acting as an adhesive. Each filled wafer is now a complete, delicate core, ready for the outer coating. The first coating is a layer of milk chocolate. The filled wafers travel along a conveyor through a curtain of tempered chocolate, a process called enrobing. The chocolate is kept at exact temperatures to ensure optimal viscosity and crystallization. Too hot, and it will be too thin and won't set properly. Too cold, and it will be too thick or bloom later on the shelf. The enrobing tunnel applies a uniform coat of chocolate that covers the wafer sphere entirely. Immediately following enrobing, the still wet chocolate is dusted with finely chopped, roasted hazelnut fragments. This is done through a synchronized nut dispenser that sprinkles fragments over the rotating, chocolate-covered spheres. The particles adhere instantly to the tacky surface, forming the crunchy outer texture that defines the Ferrero Rocher bite. From there, the products enter a refrigerated cooling tunnel to crystallize and harden the chocolate coating. This tunnel is kept at a consistent low temperature, typically around 10 to 12 degrees, with humidity controls to ensure shine and stability. Once fully cooled and set, the Ferrero Rochers pass through a final inspection system. High-speed vision cameras scan each sphere for cracks, missing nut fragments, or uneven coatings. Those that fail to meet visual standards are removed automatically by pneumatic diverters. The acceptable pieces then move into one of the most iconic parts of the process: foil wrapping. Ferrero's wrapping process is instantly recognizable. Each sphere is wrapped in a piece of gold foil, folded tightly by high-speed rotary wrapping machines that spin the foil around the product in a process similar to a ballet. The wrapping must be secure but not crumpled, an art that's perfected through decades of machine design and precision calibration. A paper band with the Ferrero Rocher logo is heat glued around the equator of the foil, acting both as branding and as a seal of authenticity. Wrapped Rochers are then gently placed into brown fluted paper cups, which not only help with presentation, but also protect the spheres from scuffing. Robotic pick-and-place arms transfer the wrapped products into their cups and arrange them into trays or gift boxes. These boxes may contain 3, 12, 24, or even 48 pieces, depending on market and seasonal packaging. Secondary packaging lines group the gift boxes into cartons for shipping. These cartons are automatically assembled, packed, and sealed using robotic case packers. Once completed, the cartons are barcoded, weighed, and stacked onto pallets by robotic palletizers, then stretch wrapped and scanned into inventory. From here, they enter climate-controlled storage warehouses, awaiting shipment to distribution centers around the world. Of course, quality control is continuous throughout the entire process. Every batch of cream filling is lab tested for fat content, viscosity, microbial load, and texture. Wafer shells are tested for brittleness and moisture content. Chocolate is sampled for bloom potential, fat migration, and melting point accuracy. Finished products are subjected to sensory panels who evaluate every aspect of the bite, from crunch to melt to aftertaste. Behind all of this is a digital infrastructure that ties everything together. From syrup cookers to nut roasters to packaging robots, the plant is run by integrated SCADA and MES systems. These systems monitor temperature trends, downtime events, ingredient usage, and traceability data in real time. Each product can be traced back to its lot of hazelnuts, batch of chocolate, and shift team, allowing full accountability and rapid response in case of any deviation. What's more, Ferrero production plants place a strong emphasis on food safety. They are certified to international standards such as ISO 22000 and FSSC 22000, and operate with strict allergen segregation, hygiene zoning, and air filtration systems. Operators wear full protective gear, and certain areas are restricted to minimal human presence to reduce risk of contamination. Sustainability has also become a central pillar of Ferrero's operations. The company has invested heavily in traceable and responsibly sourced hazelnuts and cocoa. Many factories are now equipped with heat recovery systems, water recycling units, and energy-efficient machinery to reduce the environmental impact of confectionery manufacturing. Incredibly, this entire process, from nut to wrapped product, can happen in under 2 hours. That's 2 hours to roast, fill, coat, wrap, and package what looks like a handmade luxury. But it's not magic. It's manufacturing at its most precise. Every movement of every machine, Every gram of chocolate, every foil fold, is measured, managed, and monitored. The result is consistency across countries and climates. A Ferrero Rocher purchased in Rome will taste the same as one bought in Dubai, Tokyo, or Toronto. That uniformity is achieved not through simplicity, but through complex synchronization across ingredients, machines, and human craftsmanship. From a distance, Ferrero Rocher production might seem effortless, but it's anything but. It's a feat of edible architecture, where layers are stacked with millimeter accuracy, flavors balanced with chemical precision, and every aspect of the product calibrated to evoke delight, bite after bite. In a world of mass production, Ferrero has mastered the art of small indulgences at scale. Each gold-wrapped sphere is a symbol of how far food science and industrial artistry can go, not just to make chocolate, but to make joy. For over a century, Hershey's has been America's chocolate. With its iconic square segments, sweet creamy flavor, and unmistakable aroma, the Hershey's milk chocolate bar has become a symbol of comfort and nostalgia. But few realize how many complex steps, both agricultural and industrial, go into creating each one of those neatly molded rectangles. From cocoa plantations to high-tech factories in Pennsylvania and beyond, the making of a Hershey's bar is a feat of logistics, chemistry, and precision food engineering. It all begins thousands of miles away from the factory floor, in the equatorial regions where cocoa trees thrive. Theobroma cacao, the tree that produces cocoa pods, is cultivated in countries like Ghana, Côte d'Ivoire, and Ecuador. Each pod contains 20 to 40 cocoa beans encased in a sweet pulp. After harvesting, farmers ferment the beans under banana leaves or in wooden boxes for several days. This natural process transforms the bitter, raw seed into a flavor precursor for chocolate, deepening its complexity. The fermented beans are then sun-dried, bagged, and shipped by container vessels to Hershey's processing facilities. Upon arrival, the beans are cleaned to remove debris and sorted by origin, size, and quality. Each origin brings its own flavor profile. Ghanaian beans offer classic cocoa depth, while Ecuadorian beans may bring floral or fruity notes. The blending of these origins is what allows Hershey's to maintain a consistent, recognizable flavor year after year. Once cleaned, the beans enter the roasting drums, massive rotating steel cylinders where they are slowly roasted at controlled temperatures. This step develops the final flavor of the chocolate, similar to roasting coffee beans. Temperature and time vary depending on bean type, but typically range between 120–160 degrees Celsius for up to 45 minutes. As the beans roast, their shells become brittle, and the internal nibs, the part used to make chocolate, develop their signature aroma. The roasted beans are passed through a winnowing machine, which cracks them open and uses airflow to separate the light, papery shells from the heavier nibs. The nibs are now ready to become chocolate. They are ground into a thick, dark brown paste known as chocolate liquor, a 100% cocoa mass that contains both cocoa solids and cocoa butter. Despite the name, there is no alcohol in this liquor, just pure ground cocoa nib. From here, the real engineering begins. The chocolate liquor is combined with milk powder, sugar, and additional cocoa butter in large mixing tanks. The exact formula is proprietary, but we know Hershey's is famous for its milk-forward flavor and slightly tangy finish. That tang is believed to come from a special milk treatment process developed by Milton Hershey himself, involving controlled lipolysis. Essentially, the development of specific flavor compounds by partially breaking down milk fats under heat. Once the ingredients are mixed into a coarse paste, the mass is sent to 5-roll refiners, large steel roller mills that gradually grind the chocolate mixture down to a particle size of roughly 20 microns. This microscopic consistency is what gives chocolate its velvety texture. If the particles are too large, the chocolate feels gritty. Too small, and it may clump or fail to release flavor properly. Each roll in the refiner is set with increasing tightness to achieve a uniform grind. After refining, the chocolate is still dry and powdery. To transform it into a smooth liquid, it enters the conch, a key piece of equipment in chocolate making. The conch is a heated, agitating chamber where the chocolate mass is kneaded for hours. This process drives off residual moisture and undesirable volatiles, improves mouthfeel, and develops the final flavor. During this stage, emulsifiers such as soy lecithin are added to improve flow properties. Once conched to specification, the chocolate is ready for tempering. This critical step aligns the fat crystals in the cocoa butter to ensure a stable, glossy, and snappy final product. Tempering involves a carefully timed series of heating and cooling cycles, typically heating the chocolate to around 45 degrees Celsius, cooling it to 27 degrees Celsius, then slightly reheating to working temperature at about 31 degrees Celsius. This allows the formation of type 5 fat crystals, which give chocolate its desirable characteristics. Now tempered, the liquid chocolate is ready for depositing. It flows into stainless steel depositors, which dispense precise volumes of chocolate into bar molds. Each mold is preheated slightly to prevent premature crystallization and is vibrated to remove air bubbles and level the chocolate surface. Once filled, the molds enter a cooling tunnel, a refrigerated chamber where the chocolate solidifies into its familiar form. After cooling, the molded bars are ejected from the molds by gentle air pressure or mechanical release. Each bar is then conveyed to a high-speed wrapping line. For the classic Hershey's milk chocolate bar, this involves two layers, an inner foil or paper liner and an outer printed sleeve. Wrapping machines fold and seal the bars at speeds of hundreds per minute, using heat sealing and cold gluing methods. Each bar is also inkjet printed with a production code for traceability and inventory control. Wrapped bars are then counted, stacked, and loaded into cartoning machines for retail multi-packs or into larger cases for warehouse distribution. Robotic arms and conveyors carry the cartons to palletizers, which arrange them onto pallets in precise patterns. Pallets are stretch wrapped, labeled, and scanned into warehouse inventory systems. Throughout the entire process, quality control is constant and rigorous. Samples from every batch are tested for fat content, sugar ratio, particle size, flavor, aroma, and shelf stability. Sensory panels perform taste tests to ensure the product matches Hershey's official flavor profile. Microbial testing ensures food safety, and all data is logged in digital batch records to ensure traceability and compliance with food safety standards like SQF, ISO 22000, and FDA regulations. Inside the factory, automation is central. From ingredient dosing and temperature control to tank agitation and mold handling, programmable logic controllers and SCADA systems monitor every parameter. Touchscreen panels give operators live insight into flow rates, cooling curve progress, and downtime tracking. These data streams not only keep the line running smoothly, but also help predict maintenance needs and optimize energy efficiency. Another remarkable component of Hershey's production is its environmental stewardship. Modern facilities recycle water used in cooling circuits, reclaim heat from conching motors, and repurpose off-spec chocolate by reworking it into other products. The cocoa shells removed during winnowing are even used as fertilizer or animal feed, reducing waste. Supply chain transparency is also part of the modern Hershey's commitment. Cocoa beans are increasingly sourced through certified sustainable programs, with investments in farmer education and ethical labor practices. Blockchain-based platforms now allow for bean-to-bar tracking, helping ensure that every bar supports both quality and responsible sourcing. Logistically, the bars are shipped to national and international distribution centers using temperature-controlled routes when needed. Warehouses use first-in, first-out inventory systems, and retailers receive shipments in compliance with demand planning forecasts. Each bar, despite traveling thousands of miles and passing through dozens of steps, remains precisely as Hershey intended. Consistent, safe, and perfectly sweet. It's easy to take a chocolate bar for granted, to see it only as a snack or a treat. But what lies behind that silver and brown wrapper is a world-class production system that balances food science, mechanical engineering, flavor chemistry, and sustainable agriculture. From cocoa farms to Pennsylvania steel, from sugar silos to foil stampers, the making of a Hershey's bar is not just about chocolate. It's about heritage, process control, innovation, and the relentless pursuit of consistency in a product that's been enjoyed by generations. In every square, you taste more than just sugar and cocoa. You taste a supply chain running like clockwork, a formula calibrated to microns, and a commitment to quality that's lasted over 100 years. A Hershey's bar isn't just made, it's built, layer by layer, process by process, from the ground up. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare, until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conches. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid over-waxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch. firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro-adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity. A testament to how food science can transform something as humble as a potato into a globally recognized snack. It all starts with the base formula, the gummy candy itself. The core of every Sour Patch Kid is a soft, chewy matrix primarily composed of sugar, corn syrup, gelatin, and various fruit flavors. These ingredients must be blended in precise proportions to achieve the specific texture that Sour Patch Kids are known for. Not as firm as gummy bears, not as sticky as fruit snacks, but perfectly chewy with a fast melt in the mouth. The sugar and corn syrup form the bulk of the candy. Sugar provides structure, sweetness, and contributes to the candy's crystal clear translucence, while corn syrup prevents the sugar from recrystallizing and keeps the final product soft and elastic. These two are delivered to the factory in bulk, sugar often in railcars or tanker trucks, and corn syrup in heated stainless steel tankers to maintain fluidity. In the batching area of the facility, massive stainless steel mixing kettles are used to combine sugar, corn syrup, and water. The mixture is heated to dissolve the sugar and initiate cooking. Industrial mixers stir the solution constantly, while steam-jacketed walls evenly raise the temperature to around 230 degrees to 250 degrees, depending on the desired consistency and final moisture content. At this stage, the mixture is highly viscous, resembling hot, liquid sugar syrup. Once the sugar solution is properly cooked, gelatin is added. Gelatin is the key protein that gives Sour Patch Kids their elastic chew. It's derived from collagen, typically from pork or beef, and arrives at the factory as a dry powder. It is hydrated in warm water in separate tanks and added to the sugar syrup only after the syrup has cooled to an appropriate temperature to avoid denaturing the gelatin. This step transforms the hot sugar mixture into a viscoelastic candy base. At this point, citric acid and tartaric acid are introduced. These two organic acids are what provide that first intense sour kick when you bite into a Sour Patch Kid. They are used at very specific levels. Too little, and the candy loses its iconic tang. Too much, and the texture or shelf stability may be affected. Food scientists spend years perfecting this balance. In addition to acidulants, artificial and natural fruit flavorings are also added, usually concentrated solutions of compounds that mimic cherry, lemon, lime, orange, blue raspberry, and other classic flavors. Color is next. Each flavor of Sour Patch Kid is dyed with specific food-grade colorants. These are either synthetic or naturally derived, like beet juice or turmeric extract, depending on the formulation and market regulations. These colorants are added to the mix during the blending phase in tightly controlled amounts to ensure vibrancy and uniformity across batches. Once the hot candy mixture is fully mixed, it is ready to be molded. Sour Patch Kids are molded using a starch mogul system, a technique used for generations in gummy candy manufacturing. The starch mogul line begins with large trays filled with cornstarch. These trays pass under a stamping head fitted with dozens of Sour Patch Kid-shaped molds. The stamps press into the starch, forming hundreds of identical candy-shaped impressions per tray. The hot, syrupy candy mass is poured into these impressions using heated depositors. The candy flows smoothly into each cavity, forming the familiar, tiny humanoid shape. These trays, now filled with thousands of candy molds, are stacked and moved into drying rooms, also known as curing chambers. Here, the candies rest for 24 to 48 hours in warm, dry conditions. The cornstarch helps wick away moisture from the candy, allowing it to firm up without collapsing or becoming sticky. During this curing period, the gelatin sets fully, giving each candy its final chewable texture. After curing, the trays are sent to a destarching station. Here, the starch is separated from the candies using rotating sifters and vibration tables. The excess starch is collected, filtered, and reused in future molding cycles. The Sour Patch Kids, now fully formed and firm, are tumbled through gentle conveyors to remove residual starch. Now comes the most distinctive part of the process, the sour sugar coating. This is what gives Sour Patch Kids their unique mouth-watering appeal. The coating consists of a blend of fine granulated sugar, citric acid, and tartaric acid. The finished candies are placed into large rotating pans or coating drums, similar in appearance to cement mixers, but designed specifically for food products. As the drums rotate, the candies tumble over one another, while a fine mist of water or sugar solution is sprayed lightly to help the sour powder adhere. Simultaneously, the sugar acid blend is sprinkled in. The result is a uniform, crystalline coating on every piece. Timing and rotation speed are key here. Too much coating and the candy becomes overwhelming and sticky. Too little and the signature tang is lost. Factory technicians carefully monitor coating weights and perform quality checks throughout the shift to ensure product consistency. After coating, the candies are passed through a drying tunnel or cooled in ambient air to set the coating. They are then conveyed to an inspection area where cameras, sensors, and sometimes human inspectors check for shape, color, and coating uniformity. Any malformed or off-spec candies are removed from the line. Now it's time to package the final product. Sour Patch Kids are typically packed into portioned pouches, multi-serve bags, or retail cartons. The packaging line begins with form fill seal machines, high-speed systems that unroll printed plastic film, form it into pouches, Fill each pouch with a measured weight of candy, and then seal it shut using heat. These machines are calibrated to ensure each pack contains the right amount of product and is sealed airtight for freshness. The sealed pouches are then coded with date stamps, batch numbers, and sometimes QR codes for traceability. They are dropped into shipping cartons or display cases, depending on the destination. These cartons are weighed, barcoded, and stacked automatically onto pallets. From there, the pallets move to temperature-controlled warehouses, where they await shipment to stores, vending distributors, movie theaters, and supermarkets. Throughout the factory, food safety is the top priority. Every step, from ingredient receiving to packaging, is conducted under good manufacturing practices. Workers wear protective clothing, hairnets, and gloves. Equipment is cleaned between production runs. Acid-resistant stainless steel and food-grade plastics are used throughout the facility. Environmental controls manage humidity and air filtration to ensure cleanroom-level hygiene in production zones. Sour Patch Kids production also involves detailed analytical testing. Random samples are pulled from each batch and tested in quality control labs for pH, moisture content, acid levels, color uniformity, texture, and shelf life stability. Sensory panels evaluate flavor consistency and sour-sweet balance. If any parameter is off, adjustments are made in the next batch, or the lot is held for investigation. As candy demand has grown, the process has become even more efficient through automation and smart technology. Modern factories use real-time data monitoring systems to control temperatures, mixer speeds, and depositor rates. Predictive maintenance software ensures machinery stays operational. Ingredient inventory is tracked digitally, and computerized dosing systems eliminate human error in weighing acids or colorants. Sustainability has also become a key consideration. Factories producing Sour Patch Kids increasingly aim to reduce water use, lower energy consumption, and source gelatin from suppliers who practice ethical sourcing. Even the packaging films are being redesigned in some regions to be recyclable or biodegradable. When the candy finally reaches store shelves, it has already traveled a long journey, from raw gelatin and sugar to the smiling, sour-coated figures we all recognize. Each bite delivers not only flavor, but the culmination of chemistry, engineering, and candy artistry. The sour then sweet experience isn't just a slogan, it's a precisely engineered sensory journey that begins with a sharp, puckering acid hit and fades smoothly into fruity, mellow sweetness. The process begins with the core ingredients: sugar, corn syrup, water, flavorings, and colorants. These are the building blocks of Jolly Ranchers, but the way they are combined and treated in the factory determines the final product's success. Sugar and corn syrup are delivered in bulk to the manufacturing plant, sugar often in powder or granulated form, and corn syrup as a thick liquid shipped in insulated tanker trucks to keep it warm and flowable. In the batching room, large stainless steel kettles are used to combine sugar, corn syrup, and a small amount of purified water. The goal is to dissolve the sugar and initiate a high-heat cooking process that transforms these ingredients into a highly concentrated, clear candy base. This cooking step is key. Jolly Ranchers are a type of hard candy, which means the sugar mixture must be cooked to what's known in confectionery as the hard crack stage, around 300 degrees to 310 degrees. These cooking kettles are jacketed with steam coils or electric heating elements that allow precise temperature control. As the mixture heats, the water begins to evaporate and the syrup thickens significantly. This evaporation is critical. It's what ultimately leaves the candy with such a low moisture content that it becomes glassy and brittle once cooled. Industrial stirrers keep the mixture agitated to ensure even cooking and prevent hot spots or scorching. As the syrup approaches the target temperature, automated sensors closely monitor the heat and viscosity. If the temperature is even slightly off, the final texture of the candy could be compromised. Undercooked syrup results in a sticky or chewy texture, while overcooked syrup becomes too brittle or may develop a burnt flavor. Once the sugar syrup reaches the perfect consistency, it's time to add the key components that give Jolly Ranchers their personality: flavor and color. The candy base is divided into smaller batches, each destined to become a different flavor. cherry, watermelon, green apple, blue raspberry, grape, and others. Each batch is transferred to flavoring tanks or mixing troughs where concentrated food-grade flavorings and dyes are added. These flavor compounds are highly concentrated and added in very specific ratios. Natural and artificial flavorings are used depending on the formulation. For example, a cherry Jolly Rancher might include benzaldehyde for that sharp, almond-like cherry punch, while green apple flavor could rely on malic acid esters for its tart kick. The colorants are also carefully chosen to match the expected visual identity of the flavor. Red 40, yellow 5, blue 1, and other FDA-approved synthetic dyes are often used in varying combinations to produce the vivid hues. Mixing must be fast and efficient at this stage because the candy syrup is still extremely hot and starts cooling quickly. Mixing arms or ribbon blenders integrate the flavor and color without introducing air bubbles, which would compromise the candy's clarity and structure. At this point, the flavored and colored syrup begins to thicken rapidly and takes on the consistency of hot, pliable taffy. Timing is critical. If it sets too quickly, it becomes unworkable. The next step is forming. Unlike many other candies that are molded in starch trays, Jolly Ranchers are formed using a process known as rope forming and die stamping. The hot candy is transferred onto cooling tables or through temperature-controlled rollers where it is shaped into thick, cylindrical ropes. These ropes are slowly cooled as they pass through stainless steel rollers and conveyors. The goal is to bring the candy down to a workable temperature where it can be cut and stamped, but not yet hardened completely. Once the candy ropes are at the right consistency, they pass through a forming machine fitted with precision dies. These dies stamp and cut the candy into individual pieces, each with the familiar oblong pillow shape. The forming machine applies enough pressure to ensure a clean cut, but not so much that it distorts the candy's surface. This is a delicate operation, as the candy is beginning to crystallize and solidify rapidly. The cutters must be kept heated or treated with food-safe lubricants to prevent sticking and preserve the clean edges of the final product. After forming, the individual Jolly Ranchers move on to a cooling conveyor system. These long, slowly moving belts expose the candies to progressively cooler ambient air or cooled forced air, gradually lowering their internal temperature. This slow cooling is important to prevent cracking and to ensure the surface remains glossy. If cooled too quickly, internal stresses could form, making the candy brittle or causing it to become cloudy. Once fully cooled and solid, the candies head to the wrapping stage. Each Jolly Rancher is immediately wrapped in a specially designed waxed film or polypropylene-based wrapper that prevents sticking and maintains freshness. Wrapping machines operate at extremely high speeds, feeding candies into synchronized rollers that twist wrap or fold seal each piece. The wrappers are pre-printed with branding, flavor indicators, and batch codes for traceability. The wrapped candies are then collected into large bins or counted into packaging units. Depending on the product line, Jolly Ranchers might be bagged into share-size pouches, fun-size treat bags, or bulk cartons. Form-fill-seal packaging equipment handles this part, weighing exact quantities of candies, dropping them into bags formed from a continuous roll of printed film, then sealing the bags with heat to make them tamper-evident and shelf-stable. As the candies are packaged, quality control plays a key role throughout the process. Random samples are taken and tested for color accuracy, size uniformity, hardness, and moisture content. Hardness tests may involve durometers or similar equipment that measures resistance to pressure, ensuring the candy has the right glass-like firmness. Flavor panels may also evaluate taste intensity, checking for flavor balance and clarity. If a batch is found to be off-spec, it may be rejected, reworked, or diverted to secondary markets. Behind all this precision lies rigorous food safety protocols. Workers wear gloves, hairnets, and lab coats in production areas. Machines are sanitized regularly, and allergen controls are in place even though Jolly Ranchers typically contain no nuts, dairy, or gluten. Hazard analysis and critical control point systems are used to identify and mitigate risks at each step of the process. From the moment the sugar is received to the point where a wrapped candy is sealed in a bag, Every movement is monitored and recorded for traceability. Additionally, modern Jolly Rancher production facilities are incorporating automation and smart factory technologies. Recipe management systems ensure precise ingredient dosing, and digital controls allow managers to adjust batch temperatures and cooking times from central dashboards. Optical sensors inspect wrappers for misprints. Even the temperature and humidity of production rooms are computer controlled to maintain consistent output regardless of the season or climate outside. Sustainability is also being addressed in newer production lines. Energy-efficient kettles and heat recovery systems help reduce fuel use. Water used in equipment cleaning or steam generation is recycled where possible. Wrapping materials are being developed with recyclability in mind, and many facilities are exploring biodegradable or compostable film options. The finished Jolly Ranchers, now bagged and boxed, are stacked onto pallets and moved into climate-controlled warehouses for distribution. These candies are remarkably stable, with long shelf lives due to their low moisture content and protective wrapping. This makes them ideal for global shipping. From there, they head to supermarkets, convenience stores, vending machines, and movie theaters all around the world, ready to deliver that unmistakable burst of sour cherry, green apple, or blue raspberry flavor. It all begins with the selection and preparation of the raw ingredients. At the core of every Haribo gummy candy is a combination of sugar, glucose syrup, gelatin, citric acid, fruit flavoring, and food coloring. These ingredients must be carefully sourced and managed to ensure the consistent taste, texture, and appearance that consumers expect. Sugar and glucose syrup form the base of the gummy. These are typically delivered to the Haribo factory in large quantities, sugar in bulk containers or silos, and glucose syrup in insulated tankers to maintain fluidity. In the production facility, the sugar and glucose syrup are fed into large stainless steel kettles equipped with steam jackets and stirring paddles. The mixture is gently heated and stirred to fully dissolve the sugar crystals, creating a thick, sweet solution. This sugary base is the fundamental building block for all Haribo products. Once the sugar solution reaches the appropriate concentration and temperature, gelatin is introduced. Gelatin is a key functional ingredient in Haribo gummies, providing their characteristic chewiness and structure. It is typically derived from pork or beef collagen and arrives at the factory in dehydrated granule or sheet form. Before it can be added to the sugar mixture, the gelatin is first hydrated in warm water in separate mixing tanks. Once fully dissolved, the gelatin is combined with the hot sugar syrup under controlled conditions. The resulting mixture is carefully heated to a precise temperature, usually around 150 to 160 degrees, ensuring full integration of the gelatin without degrading its gelling ability. During this step, any acids such as citric acid or malic acid are also added. These acids are responsible for the pleasant tang that balances the sweetness of the candy and enhances the fruit flavors. Next, the flavorings and colors are introduced. Haribo uses a range of natural and artificial fruit flavors to create its signature gummy taste profiles. Each flavor, lemon, orange, raspberry, pineapple, and apple, among others, is blended in concentrated liquid form and carefully metered into separate batches of the hot candy mix. Food-grade colorants are added alongside the flavorings, giving each candy its bright, transparent hue. The combination of flavor and color must be exact to meet Haribo's internal standards, and flavor technicians often perform sensory evaluations during production. With the flavored and colored syrup fully prepared, it is ready for the molding process. Haribo gummies are formed using a traditional confectionery technique known as starch molding, or the starch mogul system. This process begins with large trays filled with cornstarch. A molding board presses bear-shaped cavities into the surface of the starch, creating hundreds of individual molds per tray. The hot, viscous candy mixture is poured into these molds using automated depositors equipped with multiple nozzles. Each nozzle dispenses the exact volume of syrup needed to fill a single bare cavity, ensuring uniform size and weight across thousands of pieces. The trays are then stacked and transferred to a curing room, a warm, dry environment where the candies are allowed to set for 24 to 48 hours. During this curing period, the gelatin network solidifies, giving each gummy its final elastic texture. The starch not only supports the shape, but also absorbs moisture from the surface of the candy, helping to achieve the perfect skin. Once the gummies are fully cured, the trays are sent to a destarching machine. This piece of equipment gently tumbles the trays, separating the candy pieces from the cornstarch. Vibrating screens and air jets remove any excess starch, which is collected, filtered, and reused in the molding process. The newly formed gummies, now free of starch and fully set, are inspected and prepared for the next stage. Now comes the coating process, which adds shine and improves handling. Haribo gummies are typically coated with a thin layer of food-grade wax, such as carnauba wax or beeswax, and vegetable oil. This coating is applied in rotating drums or tumblers, where large quantities of gummies are gently mixed while a light mist of the wax solution is sprayed over them. The result is a glossy surface that prevents the candies from sticking together and enhances their visual appeal. The wax also serves as a moisture barrier, helping to preserve the candy's freshness during storage and transport. After coating, the gummies pass through a final inspection phase. This includes both visual inspections by trained staff and automated optical systems that check for shape uniformity, color consistency, and size accuracy. Any defective or malformed candies are removed from the line and discarded or recycled, depending on the facility's protocols. Next, the candies move on to the packaging line. Haribo uses a range of packaging formats, including peg bags, share-size pouches, single-serve packs, and multi-flavor assortments. The packaging process begins with high-speed form-fill-seal machines. Printed plastic film is unrolled and shaped into pouches, which are then filled with a precise weight of gummies. The bags are sealed using heated jaws that bond the plastic layers together, creating an airtight, tamper-evident package. The filled bags are then printed with production information such as batch number, expiration date, and sometimes promotional codes or QR codes for consumer engagement. They are packed into cartons, stacked onto pallets, and moved to the warehouse where they await distribution. Throughout this final stage, quality control teams monitor the sealing integrity, fill weights, and print accuracy to ensure compliance with product specifications. Behind the scenes, every Haribo production facility operates under strict food safety and quality assurance protocols. These include adherence to good manufacturing practices, hazard analysis and critical control points, and ISO quality standards. Production areas are cleaned regularly, equipment is sanitized, and every batch is traceable from raw ingredient to finished product. Samples are pulled at every stage and tested in on-site laboratories for pH, moisture content, texture, and microbial safety. Modern Haribo factories also make use of advanced automation and data analytics. Ingredient dosing is controlled by programmable logic controllers to reduce human error. Sensors monitor cooking temperatures, gelatin concentration, depositor output, and humidity levels in real time. Production managers can access digital dashboards to track performance metrics and respond quickly to any deviations. These innovations not only improve efficiency, but also support the consistency that Haribo is known for. As a global brand, Haribo also customizes its recipes and flavors for different regions. For example, gummies produced in Europe may use natural colorings derived from fruit and vegetable concentrates, while US products may include certified synthetic dyes. Flavors may also vary to suit local preferences, such as blackcurrant in the UK, mango in Asia, or sour varieties in North America. Despite these differences, the core manufacturing process remains largely the same across all Haribo facilities. Sustainability is another growing focus in Haribo's operations. The company has been investing in renewable energy, water conservation, and waste reduction across its factories. Ingredient sourcing increasingly considers environmental impact and animal welfare, particularly in the sourcing of gelatin. Packaging materials are being re-evaluated to include recyclable films and reduce plastic usage. When a bag of Haribo Gold Bears finally lands on store shelves, it represents a highly coordinated blend of traditional candy-making techniques and modern industrial precision. Each chewy bear is the product of strict formulation, controlled cooking, precise molding, and sophisticated quality checks. From sugar kettle to glossy, colorful treat, the journey of a Haribo gummy is a testament to the art and science of confectionery manufacturing. While the candies may be playful and whimsical, the process behind them is anything but casual. It requires the coordination of food engineers, quality control experts, maintenance technicians, flavor developers, and packaging specialists, all working together to ensure that every handful of Haribo delivers the same beloved taste and texture, whether it's made in Germany, the United States, or anywhere else Haribo operates. This level of consistency and care is what has allowed the brand to thrive for over a century, making Haribo gummies a global favorite that continues to delight generation after generation.